Welcome to the lecture. In this lecture, we are going to discuss about the Bode plot. So Bode plot is a graph of a system's frequency response showing the magnitude and the phase shift of a system output relative to its input across the range of frequencies. So in this lecture series, we will discuss briefly across the Bode plot. So this Bode plot is developed by Hendrik Bode. So after his name, it was named as a Bode plot, and it's a graphical representation which gives a dual plot system with the help of magnitude, that is gain, and the phase plot across the frequencies. And now in this PPT, we are going to discuss about the construction rules, key frequencies, what is magnitude plots and what is phase plot, and about the stability indicators. So coming across the magnitude plots, so the Bode plot shows both magnitude, that is gain plot, and the phase plot. So here you can discuss about the gain in the decibels and phase shift in the degrees. So let us take this graph. You can see both the magnitude and the phase which is marked across the frequency response. So magnitude plot is nothing but this top plot is typically with the y-axis in decibels, and which shows how much system amplifies or attenuates signals at the different frequencies. And here in the bottom, this shows the phase lag or lead in degrees, indicating how much the output signals timing is shifted related to the input at the each frequencies. And here also another example, and these may differ according to the system's values. And here coming with the neat sketch, you can see you have the system frequency here, which is marked as long tail, and for the magnitude, that is gain, you have in decibels, and in the phase you have in degrees. So the Bode plot representation for the magnitude will be 20 log of gain with respect to frequency and feedback with respect to frequency, and for the phase it will be magnitude of, that is angle of gain of j omega into h of j omega. So these are the representations of the Bode plot with respect to the magnitude and the phase. And here we have the puzzles here, which is related to the Bode plot. Coming to the frequencies or the characteristics. So first of all, we have the few key characteristics like logarithmic scales. Logarithmic scales is nothing but both the frequency and the magnitudes are plotted on the logarithmic scale. It allows engineers to analyze the wide range of frequencies and systems behavior on a single graph. And next one is frequency response. Bode plot illustrates how a system output changes in amplitude and timing in response to a varying input frequencies, providing insight on the system's behavior. So you can see first is gain over frequency, which is nothing but the logarithmic values across the gain, and here the phase over frequency. Here it is in the phase angles and the critical point for evaluating the potential instability. So this will be marked across here. You can see for the first magnitude plot, we have the gain and the margin, which is marked across the frequency, and in the phase we have the minus 180 degree, and here also you have plotted the phase crossover frequency, and this is also in the positive and the negative frequency. Next is system analyze. Usually we use the Bode plots to determine the gain margin and phase margin, system stability and system behavior. So gain margin indicates the system stability, and in the system stability we have to define how a closed loop system will be, which is crucial for a closed loop system design. And system behavior, we will analyze how the system responds to the input signals, helping to estimate the transfer function or the diagnose issues. And next, coming to the stability indicators, yes, we have discussed this gain margin and phase margin, and we have in gain margin we can analyze how much gain can increase before stability, and in phase margin we can analyze how much phase shift can increase before the instability. So here we can see that in the gain and phase margin you have in representation of degree and decibels. Next is Why this Bode plot matters? First thing is to prevent the oscillations. So whenever a system responds, there will be surely oscillation will occur, and we are focusing on the steady state oscillation minimization. So first one is to prevent the oscillations, and second one is to improve the response. So as well, usually if we reduce this steady state error, automatically the response will be increased. So here concentrating on the higher crossover frequency. And next is noise immunity. Yes, a system should be always immune to the noise so that we can avoid the unwanted signals embedded in the signal. And construction rules, we have to go for the poles effect. We have to analyze the zeros effect, and we combine with the both the effects. We can add the slopes and phases from multiple poles and zeros, and we can apply the superposition principles. Practical example and applications, inject disturbance. So we can apply small amount of AC into the feedback loop, and we can analyze the system response, and we can measure the response. We can optimize the design, and in the practical applications you can find it out in the control systems widely used to understand the design controllers, and electrical engineers can use it for analyzing the frequency response of the circuits, and in signal processing it is used to characterize the filters and other signal processing components. So in the next series we will discuss the another Nyquist plot stability criterion with an example. Thank you.